Hi, everybody. Okay, so I wanted to share a few tips on the homework that you're working on this week. This is homework 3B in treatment planning. We're still in the same chapter in principles, chapter 23, starting on page 504. So I wanted to give you a few tips in case you haven't found them already in your textbook. The thing that's different about these cases is that we're using a different technique. So the last few cases that you've been working on have been with SSD technique, and now we're going to start calculating treatment time for SAD technique, that is isocentric. That means that the isocenter is inside the patient. This is probably what you're seeing most of the time in clinic. So the main difference now that I want you to be aware of is that the formula for calculating treatment time looks a little different for SAD than SSD. You might recall that when we were in lecture before we had to go on break, that when we account for the changes in reference dose rate at depth using SSD technique, we use percentage depth dose. However, when we're using isocentric technique or SAD technique, when the isocenter is inside the patient, we account for the change in reference dose rate at depth by using TARs or TMRs. Okay, so with that being said, the way TAR factors or TMR factors are generated is, remember, we have to put the measuring device inside the phantom. So any of the scattering that's happening inside the phantom is accounted for when we set up TAR and TMR factors. So this phantom scatter no longer is necessary. So we're not going to use the phantom scatter factor in treatment time calculations for SAD technique. We'll need the output factor or the reference dose rate. We'll need the collimator scatter, the SC, no SP, but we'll need the TAR or the TMR, and then any attenuators. Okay, so the first case will probably pretty simple for you to do. It's just a single field. There are no blocks. The depth is given. So we're going to use this formula for this case. The second case is a little different than the first case. However, it may not be very different for you if you consider what we had to do in the last homework assignment. So this time we're using two parallel opposed fields. There's no description of unequal weighting, so we're going to assume that the two fields are equally weighted. We're going to have to calculate treatment time for both fields. Now the thing here though is there's a block in the field. Now in a previous problem described a block in the field, but it told us what the blocked down area was. It told us what the effective field size would be. This time we're going to have to calculate it. So what we're going to do is we're going to take the open field size or the collimator setting, which is 12 by 15, and subtract out the blocked area. We're going to use areas here. So we're going to take the area of the 12 by 15, which is 180 centimeters squared. We're going to subtract out the area of the block, which is 3 by 4, or 3 times 4, which is 12 centimeters squared. Subtract 12 from 180, we get 168 centimeters squared. Now we're going to have to unsquare this. So to unsquare it, we need to take the square root. When we take the square root, we get 12.96 centimeters. That is, a field that has a collimator opening of 12 by 15 with the 3 by 4 block has a reference dose rate similar to a square field that would be 12.96 by 12.96. This is important because we're going to have to use both of those, the open collimator setting and the effective collimator, in our formula. So we're going to use the equivalent square of the open collimator setting, the 12 by 15, to grab the SC or the collimator scatter factor. And then we're going to use the effective field size to grab the TAR or the TMR. And so TAR and TMR tables, I believe, are available in both the principles and the con book. I think the principles book has TMR tables for COBOL, but check and make sure. So this is what the formula is going to look like for the bottom problem. We need the reference dose rate. We're going to use the collimator setting to grab the collimator scatter factor. We're going to use the effective field size to grab the tissue air ratio. And then if there are any attenuators, we're going to consider that too. Okay? All right, hope that's helpful. I look forward to grading your assignments.